How does quantum Fourier transform differ from classical DFT? Have you ever wondered how quantum computing can change the way we process information? One fascinating aspect is the Quantum Fourier Transform, or QFT, which plays a key role in quantum algorithms. So, how does it differ from the classical Discrete Fourier Transform, or DFT? Let's break it down. First, the classical DFT transforms a set of complex numbers that representing a signal from the time domain to the frequency domain. It takes an input vector of length n and produces another vector of the same length. Each element in this output is calculated by summing over complex exponentials with negative exponents. On the other hand, the QFT operates on the amplitudes of a quantum state vector made up of n quantum bits, or qubits. Here, the vector length is n, which equals to raised to the power of n instead of producing a classical vector. The QFT transforms the quantum state into another quantum state. The amplitudes of this new state correspond to the Fourier transform of the input amplitudes, using a positive exponent convention and including a normalization factor. Now, let's talk about computational complexity. The classical DFT typically requires time proportional to n multiplied by the logarithm of n, which is quite efficient with fast Fourier transform algorithms. In contrast, the QFT can be executed using a number of quantum gates that scales as the square of n, or the logarithm of n squared. This means the QFT can be exponentially faster than the classical DFT for larger input sizes, especially when the output is utilized within a quantum algorithm without measuring the entire output state. However, if you try to measure all output amplitudes to get a complete classical result, the complexity jumps back to being similar to the classical DFT, losing that quantum speed advantage. When it comes to implementation, the classical DFT is a numerical algorithm that runs on classical computers. In contrast, the QFT is implemented as a quantum circuit. This circuit consists of a sequence of quantum gates, including Hadamard gates to create superpositions, controlled phase rotation gates to apply phase shifts, and swap gates to reorder qubits. This setup takes full advantage of quantum parallelism and entanglement. In practical terms, the classical DFT is widely used in digital signal processing for analyzing periodic signals. Meanwhile, the QFT is essential in quantum algorithms like Shor's algorithm for factoring large numbers and quantum phase estimation. It allows for efficient extraction of periodicity information encoded in quantum states, something that the classical DFT struggles with when dealing with large inputs. To sum it up, the Quantum Fourier Transform is fundamentally different from the classical Discrete Fourier Transform in its operation, computational complexity, and implementation. It works on quantum states rather than classical vectors, providing a significant speed advantage in specific tasks thanks to quantum parallelism. This makes the QFT a foundational element in quantum computing software and algorithms.